Now that we've defined a composition of functions, we'll use that idea to explore the inverse of a given function of a particular type, a function that's one-to-one. And that's a topic of section 5.2. So in this section, we determine whether a function is one-to-one or not. We find in graph inverse functions based on points, based on graphs, and more pragmatically based on equations of functions. So the formal definition of a one-to-one function is one-to-one if any two different inputs in the domain correspond to two different outputs in the range. That is, if x1 and x2 are different inputs, then the outputs, f of x1 and f of x2, are different. Different inputs yield different outputs. Schematically, here's a one-to-one function giving its domain and range. Each of these different inputs, x1, x2, x3, corresponds to a different output, y1, y2, y3. Here's a not one-to-one function. Different inputs, x1 and x2, both yield the same output, y1. A squaring function would do something like that. A squaring function takes both 2 and negative 2 to 4. 2 squared is 4, negative 2 squared is 4. So not a one-to-one function. Another possibility just with these little diagrams is we could have, instead of two x values mapped to the same y value, we could have one x value mapped to two different y values. Well, that's not even a function. You can't have a single input have two different outputs in a function. It violates the vertical line test if we had more of a graph of the thing. But functions don't have different outputs, two different outputs for the same input. So it's this idea that we're interested in. We're interested in this one-to-oneness. Let's look at some examples based on these diagram type ideas. We started the idea of a function originally by looking at these little mappings of this sort. Determine whether the function is one-to-one. Well, function's one-to-one if two different inputs in the domain correspond to two different outputs in the range, and the arrows indicate the function outputs. No two arrows converge on the same element of the range, so we got a one-to-one function. Distinct arrowheads over here at the 4 different outputs, so one-to-one function. Consider number 16. Is this a one-to-one function? Well, same idea, except this time we do have two arrows from the left converging on the same point in the range. John is mapped to Phoebe and Chuck is mapped to Phoebe. So this is not a one-to-one function. Two different outputs yield exactly the same, two different inputs, John and Chuck, yield exactly the same output. And that's a function, but it's not a one-to-one function. Returning to the notes. Just as we had a vertical line test for functions, we stated this in theorem 2.2.a, you'd look at a graph and consider whether or not it was the graph of a function by seeing if it passed the vertical line test. We can also test a function to see if it's one-to-one with a horizontal line test. The proof really follows directly from the definition of one-to-one functions. So we'll just state it as theorem 5.2.a. If every horizontal line intersects the graph of a function in at most one point, then f is one-to-one. So the horizontal line test is a quick way to test a function to see if it's one-to-one. The vertical line test is a way to check the graph of an equation to see if it's an equation that represents y as a function of x. Here we're assuming we do have the graph of a function, and we're testing it for the additional property of one-to-oneness. Number 22 says, consider the given graph of function f Use the horizontal line test to determine whether f is 1 to 1. Okay, this is one of those I've complained about in the past. Assuming the pattern that appears to be established in this little piece of the function here actually continues, which looks like we've got a function that's going to continue to grow in this direction at some particular rate. And it looks like it probably has a vertical asymptote here at 0. That's the intention. I would agree with you if you say that's a lot of information to extract from this little blue arc that they've drawn here. But they're meaning to indicate that this is a logarithm function. Functions we'll encounter later in this chapter. But trust me on that, so we can answer this. The pattern continues. This doesn't subtly turn around and come back down. If it does, that's a whole different story. But if you believe that this continues downward and has a vertical asymptote of x equals 0, and that this continues to grow, then a horizontal line would intersect the graph in only one point. In fact, a horizontal line would intersect the graph in exactly one point. If this really is a logarithmic function, I might have to go to find when it takes on the value 3, I might have to go really far to the right. But the indication is it continues to grow, and it continues to grow without bound, if you'll believe me on that. This is a strictly increasing function as well. We'll talk about that here in connection with one-to-oneness shortly. But horizontal line will intersect the graph in only one point. In fact, in exactly one point for any given horizontal line. So this does pass the horizontal line test, and this does represent a one-to-one function. Quite a special one-to-one function from our perspective of chapter 5. It turns out this is going to be a log function. How about this one? It looks like this is a quadratic function. Looks like it. Consider the graph given a function f. Use the horizontal line test to determine whether f is 1 to 1. Well, horizontal line, if it's below this point here, a horizontal line is going to intersect it in 2 points, assuming the pattern continues, assuming it doesn't turn around and come back up, in which case it might intersect it in 3 points, or maybe turn around and comes back up on both sides. Assuming the pattern continues, then we get horizontal lines to intersect this in exactly 2 points. Doesn't matter, just as long as there's some horizontal line that intersects it in at least 2 points, then we violated the horizontal line test. But assuming the pattern continues, any horizontal line up here doesn't intersect it at all. Horizontal line y equals 3 intersects it at the vertex, if it is in fact a quadratic function, and intersects it in 2 points for any horizontal line y equals a constant k, where k is strictly less than 3. For example, the horizontal line y equals 0, also known as the x-axis, intersects it in 2 points. That observation alone is enough to say it violates the horizontal line test. So it's not a one-to-one function. The horizontal line test, very easy to apply. Of course, you need a graph. And by now, you know the story behind graphing. Graphing's quite a challenge. As I just suggested, we can relate the property of increasing or decreasing to the property of one-to-one as follows. Stated as a theorem, a function that is increasing on an interval I is a one-to-one function on interval I. A function that is decreasing on interval I is a one-to-one function on interval I. You might hear the terms strictly increasing and strictly decreasing. Some settings would call a function increasing even if it's a constant function. We're not using the term increasing like that. We're using the term increasing and decreasing in a sense in calculus, probably calculus 1, that will be referred to as strictly increasing and strictly decreasing. So these are definitely strictly going uphill or strictly going downhill, as we've informally interpreted increasing and decreasing for functions on intervals. Well, if they're going uphill, then a horizontal line can only intersect them in at most 1 point on that interval on which it's going uphill, and similarly for downhill. All right, the next definition is the main idea of this section, and it's the whole reason we started talking about one-to-one functions. The development here is very traditional. First, you talk about compositions of functions, as we did in 5.1. Next, you talk about one-to-one functions, as we've just done, and that's followed up by the idea of an inverse function. We're having this conversation in chapter 5 because we will introduce exponential functions in the next section. And shortly after that, we'll talk about the inverse function of an exponential function. And that's what a log function is. You'll encounter this concept again in Precalculus 2 when you start to deal with inverse trig functions. But the basic composition of functions, one-to-oneness, and inverse function stuff is these sections right here. Suppose f is a one-to-one function. Then, corresponding to each x in the domain of f, there is exactly one y in the range. That's just because it's a function. One input value in the domain yields exactly one output value in the range. And corresponding to each y in the range of f, there's exactly one x in the domain. Each y is the result of a single x value. Each y in the range results from only one x in the domain. That's the one-to-oneness property. The correspondence from the range of f back to the domain of f is called the inverse function of f, denoted as this and read f inverse. A little cautionary tale follows about that -1 there. But the idea is, if this is an x value in the domain of f, and f maps this x value over here to this y value in the range of f, then we'll define f inverse. It just does the reverse. It takes this y value over here and associates it with this x value over here. I will often say whatever f does, f inverse undoes. So f takes this x value to that y value. Well, f inverse takes the y value back to the original x value. And this just reflects the behavior on a single point, an arbitrary point in the domain of f. You'll also notice the domain of f is the range of f inverse, and the range of f is the domain of f inverse. You interchange range and domain. You'll interchange x and y values in a certain sense to give this some geometric meaning. And we'll do that shortly. So we can find inverse functions for one-to-one functions using the description of the function. I really want to do something more algebraic, but we've hit on this idea a number of times before about having functions described. Here's a one-to-one function. The domain is the states given. The range is these percents, unemployment rates as given. So we have a function mapping this domain to this range. It's 1-to-1. Can't really use a horizontal line test to test the one-to-oneness because we don't have a graph, but I can see no two arrowheads on the right-hand side converge to the same value. So that's what one-to-oneness is when we present functions like this. Okay, so the domain is the set of states, Virginia, Nevada, Tennessee, and Texas. The range is these percentages of unemployment, 5.0%, 5.5%, 6.7%, 8.5%. These are the domains and ranges of the given function, indicated by the arrows. We want the inverse of this function. All right, geometrically, graphically, I guess, we just reverse the arrows. The domain of this function will become the range of the inverse function, and the range of this function will become the domain of the inverse function. So the inverse function has this as its domain, the percentages, and it has this as its range. The inverse function has these domain and ranges respectively. The inverse function, given as ordered pairs, we originally defined a function in terms of ordered pairs. Then the inverse function is input 5.0%, output Virginia. This input yields that output for the inverse function. The input 5.5% yields the output Texas. 5.5% yields the output Texas. 6.7% yields the output Tennessee from the inverse function. 8.5% yields the output Nevada. They're listed in a different order from how they're listed top to bottom here. Here they're listed in increasing percentages, increasing input values. It doesn't matter the order, we put them inside a set. Sets have elements, they don't come in any particular order, so there's no ordering implied, but they've been listed in an order that goes in increasing input values for the inverse function. So there's what we get in terms of actually stating the inverse function from one of these diagrams. Let's do another one that's a little more symbolic. Remember, functions came to us as collection of ordered pairs satisfying certain conditions. We're told this is a one-to-one function, this collection of ordered pairs. State the domain and range of the inverse function and find the inverse function. All right, for the given function, and a function is just a collection of ordered pairs. That's why we can graph them in Cartesian coordinates. The given function has as its domain the x values, the input values, the first element in the ordered pair. So that would be -2, -1, 0, 1, and 2. There's the domain of the function, listing them in increasing order. The range would be the output values, the second coordinate, 2, 6, 8, -3, 9, or listing those in increasing order, 2, 6, 8, -3, 9. So they're all there. So that's the domain and range, respectively, of the given function. So the inverse function will have domain and range. These interchange. The domain of the inverse function will be this set, and the range of the inverse function will be that set. The domain of the function becomes the range of the inverse function, and the range of the given function becomes the domain of the inverse function. Simply interchange domains and ranges. How you going to find the function itself and how you going to express it? Well, they want it as ordered pairs, so we'll just take those ordered pairs. But remember, inputs become outputs and outputs become inputs. So an ordered pair, like the first one, -2, 2, for the inverse function, that'll become 2, -2. So we'll swap the orders on each of these. So swap the order on -2, 2 to get the pair 2, -2. -1, 6, reverse the order, becomes 6, -1. 0, 8 becomes 8, 0. 1, -3 becomes -3, 1. And 2, 9 becomes 9, 2. Again, listing them in increasing first component, first coordinate values. But again, order doesn't matter. But there's how we can represent the inverse function in this setting. All right, that's more conceptual stuff than it is algebraic stuff. We want to get into algebraically finding inverses. So you've got a formula for a function. How do you find its inverse function? Assuming the function is 1-to-1. Well, the set of output values of f is the same as the set of input values of f inverse and vice versa. That's why you do the deal with the domain of f is the range of f inverse, and the domain of f inverse is the range of f. That's why you get those interchanged. Also, I promised I'd say this, whatever f does to the input, f inverse undoes it. If f maps A to B, then f inverse maps B back to A. It undoes what f does. Sort of my terminology on that. But what that amounts to is f of f inverse of x, or f composed with f inverse of x, is simply x itself. So you had this input x, f inverse did something to it, and then f undid whatever was done to it, giving x back. Similarly, f inverse of x equals x. F takes the x value and it changes it to something. F inverse changes it back to the original input x. The book has this little diagram about inputs from various domains and how outputs are fed into the other function. And the result is a composition of two functions that produces the function x, the identity function. Just like the reciprocal of a number. The reciprocal of 2 is 1/2, because if you multiply 2 by 1/2, you get 1 back. They're multiplicative inverses. Here we're talking about function inverses. And here we're not multiplying, we're composing. The operation between the functions is function composition. The textbook makes the very relevant observation that when they write this F inverse, this, granted, it's inspired by the idea of a reciprocal, but this has nothing to do with reciprocals in terms of 1 divided by. You're finding an inverse function, and you're finding an inverse function eventually algebraically. It will undo whatever function f does. It has nothing to do with reciprocals. Don't simply take a -1 exponent. It ain't an exponent. You don't take a reciprocal, not an exponent. It's something else. The short story is just something else. It's not a reciprocal. And we'll have techniques to go through and find them algebraically here shortly. A couple more examples to illustrate these definitions. Consider f of x equals x minus 2 squared for x greater than or equal to 2, and g of x equals the square root of x plus 2. By the way, x must be greater than or equal to 0, or we'd have square roots and negatives. Verify that the functions are inverses of each other by showing f of g of x is the identity function x, and g of f of x is the identity function x. Give any values of x that need to be excluded. Yeah, there's the values that need to be excluded from the f function. And here we'll need to exclude x less than 0. We'll have to make the restriction that x is greater than or equal to 0 because of the square root. Now they've given us this restriction. It didn't come to us algebraically. We can take x less than 2 and nothing goes wrong with the algebra. Might get a square of a negative number, but we can square negative numbers. We can't allow x to be less than 2 because they told us not to allow x to be greater than 2. What do you think they're up to here? If we simply considered x minus 2 squared, consider this function. Well, that's a quadratic function. It's an opening upward parabola when we graph it. That violates the horizontal line test. This alone is not a one-to-one function. That's why they put this condition on there. What this is, with a condition in there, is we had a parabola opening upward, and then we erased half of it and kept half of it. We kept the x greater than or equal to 2 part of it. So by giving us this extra condition, they've guaranteed that the f function is a one-to-one function. The g function is a one-to-one function. Its graph is half of a parabola with horizontal axis of symmetry. So it's certainly one-to-one, but there's a restriction on what the x values can be on that one, algebraic restrictions. So let's compose them and watch the algebra happen. Take f composed with g. G of x is the square root of x plus 2. So that's f of the square root of x plus 2. Notice x has to be greater than or equal to 0. That's implied by the existence of the square root symbol. What does f do to things? It takes the thing, subtracts 2, and then squares it. So it'll take this thing, I'll put it in parentheses down here, subtracts 2, and squares the result. So we get the square root of x plus 2 minus 2, and then squared. Square root of x plus 2 minus 2 is simply the square root of x, which is then squared. Here you see x has to be greater than or equal to 0 because we can't take square roots and negatives. The square root of x squared is x itself. But remember, x has to be greater than or equal to 2 because of the existence of the square root of 2. I'm sorry, square root of x stuff that we had earlier. So this is the given values of x that we have to worry about. So indeed, f of g of x equals x, provided x is greater than or equal to 0. Let's do the composition in the other order, g of f of x. That'd be g of x minus 2 squared. Notice x has to be greater than or equal to 2 because that's the condition on the f function right there. What does g do to things? Takes the square root of the thing and adds 2. So we'll get the square root of this thing, x minus 2, quantity squared. So we get the square root of something squared, x minus 2 squared, and then 2 added. What do you get when you take the square root of something squared? You get the absolute value of the something. So we get the absolute value of x minus 2. And then the 2 added on from this term. But wait, remember, x is greater than or equal to 2. That was a condition from up here. If x is greater than or equal to 2, then the absolute value of x minus 2 is simply x minus 2. X is greater than or equal to 2, subtract 2 from both sides, we get x minus 2 is greater than or equal to 0. This is non-negative. You can drop the absolute values. Now you can simplify. So now we can cancel the negative 2 and the 2, and we get x out. This, though, is only valid for x greater than or equal to 2. So we've shown the composition. Let's be clear about what we've shown. We've shown f of g of x equals x, provided x is greater than or equal to 0. That condition came up when we lost the square root. By the way, that's all x in the domain of g. And we had f of g of x, g of f of x equals the identity function x, the second one, but that was only valid for x greater than or equal to 2. It came up from the original definition of f. But this holds for all x in the domain of f. Provided we get the composition to equal the identity function for all x in the domain of the inner function, as we did here, and as we did here, then we got ourselves inverse functions. So on the domain of the inner function, the composition yields the identity function. And that's what inverse functions do. Let's do another one. All right, that one had square roots in it. This one has quotients. Suppose f of x is x minus 5 divided by 2x plus 3, and g of x is 3x plus 5 divided by 1 minus 2x. Verify. These are inverses of each other by doing the compositions. Give any values of x that have to be excluded from the domain. Okay, we can't have division by 0, so that'll be a condition on the domain of f, and we can't have division by 0 over here, and that'll be a condition on the domain of g. So we will have those conditions. Let's take care of those at the top. Domain of f is everything except for -3/2. Right, if x is -3/2, then we got division by 0. That's got to go. And that's the only thing that can go wrong. In the f function, in the g function, same thing. Only thing that can go wrong is denominator is 0, and that happens at 1/2. So the domain of g is -∞ to 1/2. Remove it 1/2 to infinity. Similar to the domain of f in structure. All right, so now let's do the compositions. So f composed with g, that would be f of, we'll substitute the g in. Here's the g function, substitute it in. What does f do to an input? Takes the input minus 5, the input minus 5, and divides it by 2 times the input plus 3. 2 times the input plus 3. That's supposed to reduce down to x. I got a number of things I can do to approach this. We could get common denominators and simplify. I'm going to multiply by 1 minus 2x over 1 minus 2x. It's the same manipulations. Then we'll cancel the 1 minus 2x's when we distribute. We'll lose that denominator and pick up a 1 minus 2x on the 5. So I have minus 5 times 1 minus 2x in the numerator, having simplified. Same thing in the denominator. We'll cancel the 1 minus 2x in the denominator with this 1 minus 2x that gets distributed, leaving us with a 2 times 3x plus 5. There it is. And then we'll have a 1 minus 2x term that's picked up over here, but we lost some information. Remember, x can't be a half, right? Because that gave us division by 0 if x was a half. That information has been lost when we simplified to lowest terms. So we got to stick that in by hand. Notice we can plug x equals a half into this and nothing will go wrong. But we can't plug x equals a half into the previous equation because then we get division by 0. In fact, this gives us 0 divided by 0. Nonsense. So you have to put this in by hand. That's the cost of simplifying. And they wanted us to put some sort of exclusions on there. In fact, that's exactly what we're getting due to the domain of the g function. And notice g was the inner function there. Let's multiply out. So we'll get 3x plus 5 minus 5 plus 10x. Yeah. Here we'll get 6x plus 10 plus 3 minus 6x. Simplifying, see the 5's cancel. That'll give us 13x in the numerator. The 6x's cancel, giving us a 13 in the denominator. Remember, x is still not 1/2. The 13's cancel, and then that gives us x. So we're getting the composition f of g of x equals x, provided x is not a half. We're getting the composition f equals g of x on the domain of the g function. And that's what inverse functions do. Same thing, do it again, but take the composition in the opposite order. So take g of f of x. F of x was this rational function here. We'll take g of that. That would be 3 times the input plus 5 divided by 1 minus 2 times the input. The input itself is this rational function, so we get those substituted in. Let's multiply by 2x plus 3 over 2x plus 3. Ooh, if you do that and simplify, we're going to have a problem when x is negative 3/2. Right? Same technique as on the previous slide. Why would you do this? Well, to get rid of the compound fraction. We got fractions inside fractions. This is one way to get rid of them. Another is to get common denominators in the numerator and denominator. That's fine. It just takes longer. And then simplify. But we'll distribute, and that loses those denominators, introduces a 2x plus 3 on the 5 and a 2x plus 3 on the 1 over here. There that other one is. And we get cancellation here and here. So there's those two terms. There's nothing here that says x can't be negative 3/2. When simplifying, I said cancel. When we canceled and simplified, we lost that information. It's still relevant, so we got to write it out by hand. For x not equal 3/2, these are equal. For x equals 3/2, these are not equal. This one is some number and this one's undefined. So that's why that has to be set. And by the way, this relates to the domain of the inner function, the f function. Again, distribute, simplify, and we get x out again. And this is valid, provided x is not 3/2. So it worked. So we've got f of g of x equals x for all x in the domain of g. We had to throw the 1/2 out, but that's not in the domain of g. We've got g of f of x equals the identity function, except for x equals negative 3/2. That's all x in the domain of function f. So these are inverses. So there's how to show we have inverses, but a natural question would be, where did those inverses come from? How'd they figure that out? And that's the next thing we'll do. So that's how to confirm we have inverses. Well, how do you find them? Well, geometrically first, and this is a useful idea, we'll draw some pictures, but this doesn't algebraically tell us how to find inverses. Suppose we have the point AB as a point on the graph of one-to-one function f. So here's the point AB right here. So this is some point on the graph of y equals f of x. So we know b equals f of a. I mean, that's what it means to have a point AB on the graph. Means the second coordinate is f of the first one, y equals f of x, b equals f of a. But if we've got a one-to-one function, then we can talk about the inverse. And we can relate this b equals f of a equation to a similar equation, a equals f inverse of b. B equals f of A means A equals f inverse of B, provided we have a one-to-one function, and they said we do. So we get the point BA, the output and the input. Same thing, we had output and input, output and input, output and input, output and input. The order got reversed. That point AB simply became the point BA. Right, we saw an example of that earlier as well. But here we're talking about it more in terms of a y equals f of x style function and looking at graphs. So, well, that means the point BA, output and input, is a point on the graph of f inverse. Here's the point BA. So we went over A and up B. Here we've gone over B and up A. We interchanged their roles. You knew that was going to happen. That's the whole idea of inverse functions. Geometrically, these 2 points are related to each other as follows. If you'll draw the line y equals x and reflect this point AB about the line y equals x, you'll get the point BA. And similarly, if you'll reflect the point BA about the line y equals x, you'll get the point AB. They're reflections of each other about the line y equals x. We've done reflections before, but we've only done horizontal and vertical axes of reflection. Here we're reflecting about a 45-degree line through the origin. But it's the same idea. Simply reflect, and it produces these points. So geometrically, the point BA on the graph of f inverse is the reflection about the line y equals x of the point AB on the graph of f. So if you can graph one-to-one function y equals f of x, you can use this idea to find the graph of its inverse function, this idea of reflections. And that's what theorem 5.2.c says. The graph of one-to-one function f and the graph of its inverse function f inverse are symmetric with respect to the line y equals x. So in blue, we have the function y equals f of x. And they've plotted a few points on it. In red, we've got the graph of the inverse function. So we'll take this point and reflect it about the line y equals x. It means draw a line perpendicular to the line y equals x and extend it the same distance beyond the line y equals x is a distance from the point to the axis. So whatever this distance is, travel that same distance, and that's how you find mirror images. And that allows us to take these 3 points and produce these 3 points. By the way, if we get a point on the line y equals x, the inverse function will pass through that same point. Think about it like this. Whatever point this is, I don't know, maybe it's -3, -3. It lies on the line y equals x. So the x and y coordinates are the same. Maybe it's a point -3, -3. So let's take that -3, -3 and interchange the x and the y coordinates. Well, that also produces the point -3, -3. So in this process, if we ever have a point on the function that lies on this line y equals x, the inverse function will also contain the exact same point. Because you interchange the x's and the y's, well, they're the same, so you can't tell the interchanging has been done. Let's look at number 46, where they give us the graph of a one-to-one function, f, and they want us to graph the inverse function. Okay, they kindly label some points for us. Drew the line y equals x. To get the points on the graph of f inverse, we simply take the given points and interchange the x coordinates and the y coordinates. So the inverse function will contain the points, -2, -2, interchanging these. Oh yeah, we were just talking about that. It'll be the same point. The point 0, -1 on the graph of f will lead us to the point -1, 0 on the inverse function. 1, 0 on the function leads us to the point 0, 1 on the inverse function. 2, 1/2 will lead us to the point 1/2, 2 on the inverse function. So plotting those points connecting them with line segments, plotted in green here and labeled in green, except for the one that lies on the line, we'll get that mirror image type behavior. So there's a way to graph an inverse function given the graph of a function. But we still haven't dealt with algebraically finding inverses. We've dealt with graphically finding them. How you're going to algebraically find them, and we've got a step-by-step procedure to do exactly that. To find the inverse of a one-to-one function f of x or y equals f of x, perform these steps. Replace f of x with y, creating an equation with x's and y's in it. So lose the f of x, simply change it to a y, and deal with the resulting equation in variables x and y, and obtain an equation of the form x equals f of y. That is, solve for x. So replace f of x with y and solve for x. In so doing, this defines the inverse function. Implicitly, well, if you can do the solving of the equation, then you can explicitly find the version of f inverse. So solve that implicit equation for y in terms of x, having interchanged the two, to obtain f inverse as a function of x. So replace f of x with y, interchange the x's and the y's, and then solve for y. Or replace y with x and then solve for x. Stepwise, it's laid out by replacing f of x with y, interchange the x's and y's, and then solve for y. So there's a couple of ways we can process these steps. I'll try to do it as it's laid out here. And then as a third step, they have you simply check the answer by making sure the composition actually produces the value x for all appropriate x. The appropriate x in this first equation would be the x in the domain of f. The appropriate x in the second equation would be the x in the domain of f inverse of x. Okay, so let's do 3 examples to actually find these inverses and illustrate that. All right, they give us a one-to-one function, f of x equals x cubed plus 1. Find its inverse, check your answer. Find the domain and range of f and f inverse, graph them, and the line y equals x on the same coordinate axes so you can see that reflected information. Okay, so we'll follow the steps. Step 1, take y equals x cubed plus 1. We've replaced the f of x with the y. Then interchange the x's and the y's. So change the y to an x and the x to a y. That's the protocol they told us to use, so we'll do it their way. Now solve for y in this equation. Solving for y, we can subtract 1 from both sides. We get y cubed equals x minus 1. Take a cube root of both sides to get rid of the cubing. Cube root of y cubed equals the cube root then of the right-hand side, x minus 1. Cube root of y cubed is y itself. If we were taking square roots, it'd be more complicated. If we were taking squarings and square roots, then we'd have to be careful about this one-to-oneness as well. They'd have to give us more conditions. But cube roots are cleaner. And so we get y equals the cube root of x minus 1. That should be the inverse function. So we expect f inverse of x to equal that. Domains and ranges, you know what the cubing function looks like. So its domain is all real numbers. You know what the cube root function looks like. We got translations of these by a little bit. But the domain of the cube root function, the f inverse function, is also all real numbers. The domain of one is the range of the other. So we get all of these domains. And by the way, all the ranges are all real numbers for these two functions. Check it. That was step 3. So take f of f inverse and also f inverse of that. So we got to do 2 of those. F of f inverse, this is our alleged f inverse. So we'll plug that into f. F takes stuff, input, and cubes it and adds 1. So we'll cube the input and add 1. We get the cube root cubed, so that just leaves us with whatever's under the radical, x minus 1. Add 1 to it, that leaves x. This is valid for all real numbers. Right, this one's simpler in terms of the domains and ranges. And so the composition equals the identity function. In that direction, let's take f inverse of f of x. F of x is x cubed plus 1. Allegedly, f inverse is this. So we'll take the cube root of the input cube root of the input, minus 1. Do the subtraction. That leaves us with a cube root of x cubed, which is x, also valid for all x, a real number. So these actually are inverses of each other. So that takes care of finding the inverse, checking it. We found the domain and ranges of both of these, verbally at least. Now let's graph them. Okay. There's a statement formally of the domains and ranges as described. Ranges are hard to find unless you have a graph. Yeah, but the domain of one is the range of the other. And we know the domains of both of these functions. The domain of this is all real numbers. Okay, that means the range of this one is all real numbers. The domain of this one is all real numbers, so the range of that one is all real numbers. Everything is all real numbers. To graph, okay, we'll take x cubed plus 1, as you know from your previous experience with transformations. We'll take the cubing function and shift it up 1 unit, add 1 to the cubing function. That's a vertical translation up by 1 unit. And that produces this function. Got that little special point marked there. The cube root function, we know what that looks like as well. So you could take the cube root function. That would be this green function passing through the origin. If it were simply the cube root, but we don't have the cube root of x, we've got the cube root of x minus 1. That's a translation to the right by an amount of 1, treated as x minus h equals 1. That was the symbols we used back when we did transformations. And so we get the cube root function translated to the right 1 unit, and it looks something like this green curve here. Is that right? Yeah, it looks like we've got the little mirror image thing going on with these 2 points. They both cross the line y equals x here. And it looks like we got the whole reflection about the line y equals x, the mirror image about the line y equals x going on between the blue curve and the green curve. So they do indeed have the predicted symmetry with respect to y equals x between the blue curve and the green curve. You've interchanged x's and y's. Consider the one-to-one function, f of x equals x squared plus 9, where x is greater than or equal to 0. Okay, this one's only involves second power instead of third, but this one's going to be trickier because you have to impose a condition to make sure you get a one-to-one function. Find its inverse and check your answer and do the stuff we did in the previous one. So we'll follow the 3 steps. First, replace the f of x with a y equals x squared plus 9. Second, interchange x and y so that this becomes x equals y squared plus 9. Previously, we had x is greater than or equal to 0. So in this relationship, we'll have y is greater than or equal to 0. Interchanging the x and y in the definition of the function, which includes this extra little piece over here. So there's what we get, having interchanged x's and y's. Now, solve for y. Solve for y, so get the y by itself, subtract 9 from both sides, gives us y squared equals x minus 9, and y is greater than or equal to 0. Take square roots of both sides, square root of y squared is what? Absolute value of y. We get the absolute value of y equals x minus 9, but we're carrying along this condition that y is greater than or equal to 0. Good thing we are, or we couldn't get rid of the absolute value. Good thing we are, or we wouldn't have a one-to-one function. So this condition that y is greater than or equal to 0 allows us to conclude the absolute value of y is the same as y, since y is greater than or equal to 0, and we get y equals the square root of x minus 9. That should be the inverse function. Quick comment, I guess the domain of the inverse function is x greater than or equal to 9 because we can't take square roots of negatives. So we got rid of the absolute value with a justification. You don't just drop the absolute values. Many times we've gotten rid of the absolute value by dropping it. But we could equally well work the exact same problem where we take x is greater than or equal to 0 up here and change it to x is less than or equal to 0. And that would cascade down to here where we'd have y is less than or equal to 0. Well, the absolute value of y when y is negative doesn't equal y. It equals negative y. So were the problem very subtly different, you wouldn't just drop the absolute values. We're not dropping the absolute values without investigation. We're looking at what the values of y are and determining from that what the absolute value of y is. If y is positive, that's y itself. If y is negative, that's negative y. Negative times negative is a positive, and absolute values are always positive, except at 0. So we didn't simply drop the absolute value, and we wouldn't simply get y if the problem were very subtly different. But the problem we're working, we get this is the alleged inverse function. We observe the domain of that inverse function, and now we check. That was part of part A. So we'll take f composed with f inverse, alleged f inverse. Here's our alleged f inverse, and we will want to get x out for all x in the domain of f inverse, and it looks like that's what we're going to get. The f function squares the input and adds 9, so we'll square the input and add 9. That produces x minus 9 plus 9. Indeed, that equals x. Notice this is only good for x greater than or equal to 9, or else somewhere back here you got square roots of negatives. So that condition must be imposed. It's okay. That's the condition that yields the domain of f inverse. We want f of f inverse of x to equal x on the domain of f inverse, the inner function, and that's what we got. Next, consider f inverse of f of x. Reverse the roles here. We want that to equal x for all x in the domain of f. What's the domain of f? X greater than or equal to 0. Right? They impose that condition up there in their definition of the f function. All right. So f of x is x squared plus 9 with a condition that x is greater than or equal to 0. I'll stick that over here on the right-hand side. It's part of the story. F inverse takes the square root of the input minus 9. So we'll take the input, subtract 9, and then take a square root. 9 minus 9 cancels. We get the square root of x squared. That's the absolute value of x. And since x is greater than or equal to 0, that equals x itself. We didn't just drop the absolute values. We got rid of them for a reason. Had this been x is less than or equal to 0, we'd pick up a negative sign here. And we'd have a bit of a longer conversation about how we've still got an inverse of the function. So keep an eye on these input values as to whether you're getting the identity function out or not. We are in the appropriate place for x in the domain of the inverse function here and for x in the domain of the function itself here. So these really are inverses. Domains and ranges, well, we were actually given the domain of the f function. We were told that f of x was x squared minus x squared plus 9, where x was greater than or equal to, that's a little typo there, wasn't it? Yeah, that should be 0, excuse me. Oops, little error there. X is greater than or equal to 0. I will correct that. This should read x is greater than or equal to 0. Error on my typing part. And we were told that, or we discovered that f inverse of x is the square root of x minus 9. And this one required x to be greater than or equal to 9. So the domain of the original function is x greater than or equal to, 0. That was given. The domain of the inverse function, as we observed, is x greater than or equal to 9. Well, the domain of this one will be the range of f inverse, that one, and the domain of f inverse will be the range of f itself. So based on the fact that we're good at finding domains and the fact we're dealing with functions and their inverses allows us to find ranges without having a graph. So normally you find a range by having a graph. We're about to have a graph. It's because we're dealing with functions and their inverses and the behavior of the domain of one being the range of the other that allows us to find ranges. We're good at finding ranges. We're not so good at finding, we're good at finding domains. We're not so good at finding ranges unless we got a graph or there's a trick, and there's a trick in this setting. So the graphs look something like this, x squared plus 9 for x greater than or equal to 0. All right, it looks something like this. It's the parabola y equals x squared, shifted up 9 units. Oh, and we've erased the part where x is less than 0 and only kept the part where x is greater than or equal to 0. What if you kept the rest of it? Then you'd see a little mirror image going up over here, and we would fail the horizontal line test and not have a one-to-one function. So that's why they impose this extra little condition, x is greater than or equal to 0. Square root function, f inverse of x is the square root of x minus 9. That's the square root function shifted to the right 9 units, and it looks something like this. Discussing it in terms of the way we dealt with transformations in the past, the square root function was in your library of functions, if you'll recall. And indeed, these are mirror images of each other. Very plausible from the picture. This is the point 0, 9. This is the point 9, 0, for example. We could track a few more points if you like. But these are mirror images of each other. And we've established algebraically that they're inverses of each other. That's how you find inverses algebraically, by that step-by-step process. Let's see, I think we got one more, where we deal with the function f of c equals 9/5 c plus 32. We're told this converts temperature from C degrees Celsius to F degrees Fahrenheit. One quick observation here, they're using F both as a variable and as a function name. That's a little poor style, but that's what they're doing here. And we're going to do the same thing with C. We're going to use C both as a function, C of F, and as a variable. But this relates Fahrenheit temperature to Celsius temperature. Switch them around. Express the temperature in degrees Celsius C as a function of the temperature in degrees Fahrenheit. So here we've got Fahrenheit in terms of Celsius. We want it the other way around. We want Celsius in terms of Fahrenheit. We're reversing stuff. That's why this is in the section on inverse functions. They say then verify that C equals C of F really is the inverse of function F equals F of C by taking the compositions and showing you get the identity. C of F of C equals C and F of C of F equals F. The input variable is ultimately what we get on the right-hand side. The input here is C, C is the output. The input here is F, F is the output. And then they ask you, what is the temperature in degrees Celsius if it's 70 degrees Fahrenheit? Well, we'll have a formula for it. So first off, take this equation, F equals 9/5 C plus 32. Replace the kind of the F of X with Y. I said I've complained about their use of capital F both as a function name and as a variable. But we get this relationship upon replacing F of C simply with F as we were given. We'll just solve this for C. We'll subtract 32 from both sides, multiply by, divide by 9/5, multiply by 5/9 if you like, and we'll get C equals 5/9 32, 5/9 times F minus 32. Let's leave it like that, 5/9 F minus 32. I can distribute, but 5/9 times 32 is nothing interesting. It's 160 over 9. Well, let's just leave it like that. What this coefficient really tells you is the size of a degree Celsius versus the size of a Fahrenheit degree. 1 degree Fahrenheit corresponds to 5/9 degrees Celsius. So the Celsius degrees are almost half the size of the Fahrenheit degrees, is what I can extract from that just informally. But there's a formula. Part B, do the composition. Okay. So they ask us to deal with a composition. There's an absolute zero temperature. Let's overlook that and just deal with this algebraically, saying the domain of this function and the domain of this function is up here. C is all real numbers. Down here, F is all real numbers. Now, there's some physical reasons to object to that. But if we can show this works for all real numbers, then it works for some appropriate subset of real numbers. So we're going to gloss over the fact physically that there's an absolute zero. C of f of c. That would be C of f of c is what was given, 9/5 c plus 32. What does the C function do? Takes the input, subtracts 32, and multiplies by 5/9. Here's the input. The input, subtract 32, and multiply by 5/9. This is the function notation. We're not multiplying by C here. We're treating C as a function. You think that's poor style? I agree. It's easy to get confused over the notation here. I wish they would have used lowercase f's for the variables or something like that instead of the function names and the variables with the same symbols. But that's what they did. Welcome to the real world in some sense. But this could be cleaner. We'll do the arithmetic by canceling the 32 and negative 32. That leaves us with 5/9 of 9/5 c. Well, those are reciprocal, so that just leaves us with c. This is valid for all real numbers c. We got the identity out. Whatever f did to variable c, function capital C undid, and we got the variable back out. F of c of f. What's c of f? We think it's this right here. So we'll plug that into the capital F function. So the capital F function will take 9/5 of that input and add 32. 9/5 of that input and add 32. The 9/5 and the 5/9 distribute. Those cancel, leaving us with F minus 32. Over on the right-hand side, we get the plus 32. Gives us F back out. F could be anything, any real number. So these really are inverses of each other over the whole real number line. Issues about absolute zero aside. The last part says, what is the temperature in degrees Celsius if it's 70 degrees Fahrenheit? Well, we got the formula right here. We'll plug 70 in for F and see what C is. Okay, we had the C function was 5/9 Fahrenheit temperature minus 32. Plug in 70 for the Fahrenheit, and we get 5/9 70 minus 32. 70 minus 32 is 38. 5/9 of that is 190 over 9, because it's 21 and 1/9 degrees Celsius for what it's worth. 70 degrees Fahrenheit is a comfortable fall temperature, maybe. Corresponds to about 21 degrees Celsius. So the scales differ significantly at certain temperatures. And this answers their question. Actually, both of these are linear functions, but they got different slopes. So they intersect somewhere. Little bonus education. Let's find where Fahrenheit and Celsius are the same. Both are linear functions. They got different slopes. They intersect somewhere. So let's set the Celsius temperature equal to the Fahrenheit temperature. Celsius temperature, 9/5 C plus 32. It's the corresponding Fahrenheit temperature as we were given up here. So we'll set C equal to that and solve for C. Take the C to the right-hand side and the 32 to the left-hand side. We get the 32 becomes a negative 32. We'll then have 9/5 C minus C, writing it in the opposite order over here. 9/5 C minus C be 5/5 C, would leave us with 4/5 C equals -32. Cross multiply by the 5/4. Lo and behold, it produces C equals -40. So at -40 degrees Fahrenheit, we'll also have -40 degrees Celsius. That's the input value that will indicate where those functions have the same output value. It's where the graphs cross if we were to graph them on a Celsius Fahrenheit coordinate system. But -40 degrees Celsius and -40 degrees Fahrenheit are exactly the same, just for fun. And that takes care of the content of this section, and that takes care of compositions of functions in the previous section and inverse functions in this section. Next section, we'll consider exponential functions and rather shift gears. So that's a brand new topic. The reason we've talked inverse functions is once those exponential functions are introduced, we're going to want to take their inverses. So we'll take inverses of exponential functions, and those are called logarithms. We get through this exponential function stuff and this logarithm function stuff, and that'll conclude chapter 5, and that'll conclude Precalculus 1. So we're getting there. Have a nice day. I'll see you in section 5.3.